Let's take a look at the relationship between the binomial and Poisson distributions. The binomial distribution tends toward the Poisson distribution as n tends to infinity, p goes to 0, and lambda equals n times p stays constant. Here we have the binomial formula and the Poisson formula. Now we know the mean of a binomial random variable is n times p, and we know that the mean of a Poisson random variable is lambda. So if we set n times p equal to lambda, and then p equals lambda over n, and we took this value and we substituted it in for p up here, then, it might not be obvious, but as n gets really large, as n goes off to infinity, this binomial formula tends towards this Poisson. So as n goes off to infinity, and p goes to 0, because lambda equals n times p is a constant. As that happens, the binomial tends toward the Poisson. Now it's not obvious, but I do have a mathematical proof of that in another video. An implication of this is that the Poisson distribution can be used to provide a reasonable approximation to the binomial distribution if n is large and p is small. Let's look at an example to illustrate. Albinism is a rare genetic disorder that affects approximately 1 in 20,000 Europeans. Now this 1 in 20,000 is just an approximate value, but let's take it to be exact for the purposes of this question. People with albinism produce little or none of the pigment melanin. Now this manifests itself in different ways, but overall they tend to have very fair skin and very light-colored hair and things along these lines. In a random sample of 1,000 Europeans, what is the probability that exactly 2 have albinism? Well, we're looking at 1,000 people. Each individual person either has albinism or they do not. And if we are sampling randomly and independently, then this is really going to follow a binomial distribution. The number that have albinism is going to have a binomial distribution with n of 1,000, and p is the probability any one individual person has it. And that was given on the last page as 1 over 20,000. And we are interested in the probability that x is equal to 2. And so we just use our binomial formula. N choose x, so 1,000 choose 2, times p to the x, 1 over 20,000, squared, times 1 minus p, 1 minus 1 over 20,000, to the n minus x, so 1,000 minus 2. And if you put that into your calculator, we get 0.001187,965. Now let's use the Poisson approximation in this case, just to see how well it works in this particular scenario. So we would let lambda equal n times p, which is 1,000 times 1 over 20,000, which works out to 1 in 20 or 0.05. And then our Poisson formula is lambda to the x, e to the minus lambda, over x factorial. So if we want the probability that x is equal to 2, using our Poisson approximation, this is going to be approximately 0.05 lambda to the x, e to the minus lambda, over x factorial. Put that into your calculator or computer, and you'd see that this is equal to 0.001189,037. And the value we get from the Poisson approximation is very close to the true value from the binomial distribution. And that's true in this case because we had such a large n and a very small p. So the Poisson approximation is going to be very reasonable in this particular case. Here's a very rough guideline. The Poisson approximation is reasonable if n is greater than 50 and n times p is less than 5. Now, this is just a rough guideline. The approximation is going to work best when n is really big and p is really close to 0. So whether it's a reasonable approximation or not depends on your needs, but this is one rough guideline one could use. Why use this approximation? If something truly has a binomial distribution, then we should calculate probabilities based on the binomial distribution. But sometimes those factorials and exponentials in the binomial formula can become problematic to calculate if n is very large. We might end up getting some round-off error, or a computer or calculator might actually just give us an error and say you can't calculate it. That's a little bit less of an issue for the Poisson distribution. Also, a problem may be binomial conceptually, but n and p may not be known. In order to calculate binomial probabilities, we need to know n and p. Now, if we happen to know the mean number of occurrences, we could call that lambda and use that in a Poisson formula, provided we knew we had a very large n and a very small p. But we don't need to know what those actual values are, we just need to know the mean number of occurrences.